Okay, folks, this is Tom from anti-proton.com, and I'm back to you a week later. I'm going to show you the results of my rain sample. And first off, you're probably wondering why this is from check source and not sample. This is a sample of Cs137 that I have a check source that I bought. And I put this here because last time I was talking about cesium in the rain, and I showed an actual check source spectrum like this. And somebody took that picture, which was obviously from a check source, and tried to claim that that was somehow a spectrum of my rain, which if I saw a spectrum that looked like this, I'd probably jump out the window and run away. So I put this up here so to make it more inconvenient for them to try to rip it out of my video and do that again. That was really annoying. But anyway, as you can see with cesium-137, you're looking for a peak right here at 661.66 kiloelectron volts. And you're looking for a peak right there at 32 kiloelectron volts. Those are the two primary ones that you're looking for with gamma spectroscopy. Okay. And this, of course, is always a trouble when you're dealing with radon washout because, well, this is uranium. Put that there so nobody claims anything. This is uranium, so uranium obviously is radon washout. But if you recall from radon washout, you get these three guys right here, the 214, 214, 214, same thing. And you get bismuth 214 right here. And the point I wanted to make with that is you see that green area that was in the other one? It shows a similar area in the other one, and they kind of overlap a little bit. So basically put bismuth 214 can throw off detection of cesium-137 big time. In fact, a really poorly calibrated isotope detector could potentially even think it was cesium-137. Bismuth 214 is in every single soil sample I've ever tested. It's really, really commonplace. So anyway, let's get away from this and get into the actual sample. Boing, boing. We can get rid of this. Wow, look at the big one. Okay, so here's the rainwater. Radon progeny has been given time to decay out. It took days, but there it's gone. There it is in logarithmic view. Switch to linear. It's a little easier to see, in my opinion, in linear. Now, you'll see that the detector made this. This is actually from the detector, the lead in the detector. See the red area? And as you can see here, there's plenty of spectrum going all the way across here. Gamma rays of all types and X-rays hit this. So this kind of all over the place kind of spectrum is usually the result of beta and alpha emitters being mixed in there. And keeping in mind that this was a sealed sample container, so all those alpha and beta emitters are still inside of the sample from the radon. They're there. And remember, folks, radon doesn't mean safe. Radon is in our rain right this moment. It's probably actually more dangerous for us than the cesium-137 because the CDC actually confirms approximately 20,000 cases of lung cancer a year from radon. I don't know how many will actually come from cesium-137, how many have from all the thousands of nuclear weapons set off. Yeah, 1,000 at least nuclear weapons set off around the world above ground. And of course from Fukushima, from Chernobyl, from Windscale, from 3 Mile Island. Fukushima is not the only thing that ever blew up. There's a bunch of them actually. And for the total cesium that's been cesium-137 that's been dispersed across the entire world, who knows what the total figure is? It could be more, it could be less. But I can tell you for a fact that there are approximately 20,000 cases of lung cancer per year from radon per the Center for Disease Control. So there you go. So here's where we should be looking right here. In fact, pretty close. Where is it? Where is cesium-137 supposed to be? Right there. So right here, excuse me, this right here should be cesium-137. And as you see, there's not really much going on there, but there is a little bit of a peak dead on for 32 kiloelectron volts right there, almost directly dead on. Could that be an indicator? Well, we took a background spectrum. This is a background with nothing in it but an empty detector. And during the background, you'll notice that there's that similar 32. It's almost 32, it's close. There's not a lot going on over here for cesium-137's area, just a little bit. So what you do is you take the sample. Where's the sample? You take this sample and you remove this background from it. Both of these are 6-hour runs. The result is one of these two. I'll open them both up and look and see what they are. Ah, here we go. I'll show you this one first, and I'll show you the other one. I'm not hiding it. I'll show it to you in just a second. This is the entire area still highlighted. I don't know why I don't have this one highlighted, but it's 32 keV, so let's go find it. 32, right there. And as you can see, there's a little bit of a rise right at 32. It's not much. Let's go to linear and take a look. See what I mean? It's not much at all, but there's a little bit of a rise. Could be something. There's, let's see, where's 662? That's 696. 670. Where is it? There. It's not particularly apparent. Let's zoom in. Let's see, how do we zoom in? Okay, I can't remember how to zoom in. Zoom. Shift up. Okay, well, there you go. So here it is. This is where Cs137 should be, and as you can see, there's not a lot going on here. It's not particularly high. It's not particularly higher than anything else. Let's put a grid in. See what I mean? There are other things, other random things here that are equally higher, if not more so. Look at that. In fact, that's actually an unimportant looking region where the Cs137 should be. But that's odd because I usually can find Cs137 in rain samples. It's usually there. It's not the primary cause of why the Geiger counter goes crazy in the car, which was the whole point of my video. I don't know why everybody missed that point. It seemed so obvious, but the point was not to say it wasn't there. I've actually been saying it was there from day one, so it's sort of always insulting to me when people say that I'm denying it, because that's the point of the video, is that it's there. But regardless, it's obviously not why the Geiger counter is going crazy. Now, cesium, I talked to a chemist about this because I'm not a chemist. And people kept saying, well, what if it's evaporating? And I was thinking about, radon forming radon hydroxide the way cesium forms cesium hydroxide, and I found out I was wrong. Radon does not form radon hydroxide. I got schooled by chemists. Well, good for me. I don't know if the guy that schooled me, so to speak, was a chemist, but I went and talked to a chemist afterwards, and I got schooled again. So yeah, either way, I got schooled by a chemist. But the chemist explained to me that cesium, the cesium in general, it does not evaporate easily in water. It's not that it can't, but it doesn't usually, because it dissolves very well in water, like extremely well in water. Basically put, I don't remember the amount off the top of my head, but it was something like 300 grams per liter or something like that. It dissolves right into water. And that means that for standard pressure, standard temperature, if the water's still there, the cesium's still there. Once the water has been evaporated away, there will probably still be cesium there. It can evaporate into the air, and heat and pressure are what usually does that. That's one of the reasons it evaporated away from the reactor when it first happened, because there's a lot of heat and a lot of pressure. But you remember the yellowish salts that were forming in the outside of the reactor that was shown on TV a whole bunch of times, those yellow salts? Well, those were, I believe, from cesium-137, well, not cesium-137, but cesium in general, all the various isotopes of it. And that's because it doesn't dissolve very readily, because it's like a salt. It's kind of like sodium chloride. Of course, it's obviously not sodium chloride, but it's the same sort of concept. And they're from a similar part of the periodic table as well. Now, I had a sealed sample, so it wouldn't matter anyway, but I just wanted to bring that up because somebody did bring it up, and it was a good point. What if it did evaporate? What if it was the cause of the Geiger counter going crazy and it evaporated? I didn't think it was likely, but so it was a reasonable thing to look at. You should never just discount something, so I looked into it. It wasn't true, though. Okay, so not much going on. Let's try to extrapolate what there could be, though. Let's take a guess. I was looking at this earlier, and I've come to the conclusion that if there's any at all, it's this little area right here. All right, where's the main piece of it? Right there. The main piece of it's right down the middle. See? This whole area right here, everything else seems kind of discontinuous afterwards. And I'm not taking a particularly scientific approach to this because there isn't really a scientific approach to this when you're dealing with something that's so low it's falling below the statistical mean. But basically put, let's go with 136 counts. I don't believe that's right. I don't believe there's much of any Cs137 in this at all. But to give you an idea of how I would calculate it, I did a little bit of stuff for you. Boing. The detector's area is 1,590.43 millimeters squared. You see how I got that? Pi times radius squared, the radius of my detector. And this is a drawing of my detector, sort of. It's not to scale. The drawing's not to scale, but the actual measurements are, of course. And the detector is 45 millimeters in diameter, and it's a kind of a cylinder. So pi times half of that, which is 22.5 millimeters, is equal to 1590.43 millimeters squared. So that's how much area is in the front of this in millimeters. And I drew a circle emanating from the water. This is a rough approximation, 120 milliliters of rainwater right down the middle, and it was positioned right in the middle. That was done on purpose. This is about 30 millimeters length, about 10 millimeters length to here. So we're looking at 40 milliliter. If I say milliliter, I mean millimeter. 40 millimeters length total. And we calculate this angle right here is the hypotenuse simply by Pythagorean's theorem. Hypotenuse is square root of a squared plus b squared. And so we just put in the numbers for 40 millimeters and 22.5 millimeters, and we come up with 45.89 right here. So we use the sign of that, and we end up with the opposite over the hypotenuse, which gives us a ratio of 0.49 from here to here. And then we take the inverse sign of that, and we get 29.34 degrees is the angle here. And that's in degrees. It's easier for me than radians. We multiply it by 2, we get 58.68 degrees. So the entire area emanating from the circle and out is 58.68 degrees. The reason I did that is because I can divide that by 360 degrees and figure out the ratio of this to the circle. And that ratio should remain the same when I expand this out to a sphere, 4 pi r squared geometry. It should expand right out, meaning that we should assume that whatever activity we detect against here is approximately 16.3% of the total activity coming out of here. That does not account for the linear coefficient of water, meaning that there could be a little bit higher activity, but when I did my recent analysis for the Polymaster, to detect how low I could detect on that, I discovered that the linear attenuation of energy and photons and so forth from Cs137 in water is very, very low, actually. So very little is lost, and I mean very little. This little container is only 120 milliliters. So it's not very big anyway. Let's do the math, though, and figure it out for ourselves. Okay, now we know our detector, my detector, has an energy efficiency of about 5.8% for this energy for 662.66, 5.8%, right? Well, just trust me on that. I figured it out last time I did calculations using my sample sources. And we know I did 21,600 second analysis. And let's see what we concluded here. I still say that this is way too high. I mean, this is over the top too high, because I would call the sample null. It's too low to be a confirmed detection, but it's too high for me to say that's nothing. I think it's probably some in here, but I think it's too low to quantify. But we're going to quantify it just for giggles to show you how I would calculate it. And let's just say that we believed that 136 counts we detect here are accurate. I don't think so, but let's try it. 136 counts. We're going to divide that by the time in seconds. We're going to stay in SI units, 21,600 seconds. That's 0.006 counts per second, right? Not very much. That's how many we think we've gotten. We know that we're only picking up 5.8% of them, so let's divide that by 0.058 and scale that up to 1/10 of a detection per second during that whole period of time. Now, let's get back to our little math sheet. All right, so that's that. Now, we think that that's actually 16%. So let's divide that by 0.163. We think that's actually only representative 16.3% of what's actually in the container. So we've almost gotten to a becquerel. Okay. And now we know that that's for an entire 120 milliliters. So we'll divide by 120 and get per liter, or not by liter, per milliliter itself. So per individual milliliter. Then we'll multiply that by 1,000 to get a full liter per liter. So our grand total is, we'll just kind of truncate round whatever, so 9995. So we'll call it 5.55 becquerels point per liter. All right, 5. Oh my God, that's horribly drawn. Hell, it's a conspiracy for anybody to draw this badly. Okay, well, apparently my drawing skills are so bad that it's like It should be banned in like 3 states. That's how bad it is. Now, I think that that's heavily over the top. I don't think I detected enough to quantify anything. But even if I took the maximum amount that I would be willing to put my stamp on, and I'm not willing to put my stamp on this, but if I were to take the maximum amount, it would be 5.5 becquerels per liter. And I absolutely guarantee you that your Geiger counter does not pick up 5.5 becquerels per liter, because my Polymaster, which gets a 420 count per minute background, does not pick up 5.55 becquerels per liter. I guarantee that that's not the case. It took my detector here that gets 3,600 counts per minute, 3,600 counts per minute. It took it 6 hours in careful analysis to pull out what might be 5.5 becquerels per liter. Now, baby food has a maximum in the United States legally of 50 becquerels per I believe it's kilogram. So we're a little bit lower than that right this moment. Okay, what was I going to show you? Oh, yes. Now we're going to look at a document from NASA, and this is pre-Fukushima. So if everybody thinks there's a conspiracy, keep in mind that this is from like 1994. So like the conspiracy would not have happened yet. I don't think there's a conspiracy, but let's just say there were, just for hypothetical purposes. Then this would be like 15 years before that. I don't know why they would do this, but whatever. They did an analysis of Cesium-137 in soil samples from around the United States, because fallout from every sort of thing from Chernobyl to weapons testing has coated the entire United States with Cesium-137. This is a well-known fact, and actually I don't know if it's a well-known fact. If you're into science and science things, it's a well-known fact. So that's really a poor statement. It's actually probably not a well-known fact amongst most people. Because most people that I bump into seem to believe that even 1 becquerel per kilogram of Cesium-137 is like instant death or something. I mean, you probably eat, I don't know how many becquerels worth of it per day anyway in your milk, and you probably always have your whole life. I'm not trying to say it's harmless or anything. I'm sure it's not good, but it's already there anyway. Okay. According to the analysis that was of 600 samples from around the United States, let's see, 600 samples about from 200 properties in central New York, 26 in Beverly, Massachusetts, 10 in Northern Peninsula, blah, blah, blah. They tested them in Oak Ridge, which is a pretty good place, and they found that they averaged 10 to 110 becquerels per kilogram, the highest being 700 becquerels per kilogram. So even if that was right, if I totally called that, it's still way less than 1 kilogram of soil naturally is. Now, if you don't believe this, let me zoom up here to the top and let me show you what this is. Investigations of natural variations of Cesium-137. I wouldn't really call it natural variations, because Cesium-137 is not natural. It's a byproduct material. I think that they're referring to is how it disperses itself in nature, because the whole document clearly talks about it coming from weapons testing and so on. So anyway, investigations of natural variations of Cesium-137 concentrations in residential soils, prepared for Health Physics Society, 39th annual meeting, student 3 environmental and radon session, June 28th, 1994. I'm kind of like fair using this right here. It's a documents up here by NASA, so most of that stuff's public domain anyway, but I'm not going to show you the whole thing because I can't probably do that. But you can see this address, and I'll put it in the information, and you can go there and look at it yourself, and you'll see it's all over the place. So let me just make sure that this is totally understood. I am not denying that there's Cesium-137. I have found Cesium-137. Here's a spectrum I analyzed back in 2012. And look, what's this right here? Barium-137M, that's what Cesium-137 decays into. So that's Cesium-137. Look at it right there. See how much more pronounced that is in the water? That's an actual Cesium-137 detection right there. Made by yours truly, mind you. So the person who's allegedly denying it, here's me showing it to you. I did it last year. There's a small peak right here. I think my beta filter actually cleaned out most of that. And of course you can see all the other usual suspects. They're in there too. Unknown peak. But anyway. So, there you go. This has been Tom from anti-proton.com. I don't think it's time to run for the hills yet. I think that, quite frankly, we're not really detecting very much, and I wish I could have found more. But I'm Curious to see how people will go bananas over this one. Bye-bye.